Today we'll go over Chapter 2 on the fundamental of reservoir engineering. So Chapter 2 is a revision of the rock and fluid properties. So in this chapter, we'll go through the reservoir rock properties and the reservoir rock and the reservoir fluid properties. Because in our system, we have rock and fluid, and as we mentioned last in chapter 1, you need to understand how the fluid behaves first at different pressure and temperatures, and we mentioned the PVT tests, which will be the reservoir fluid properties, and we need to understand the rock properties and how the fluid behaves in the rock system under different pressure and temperatures. So to have a full understanding of this before we move into the reservoir engineering, we need to know what are the parameters or properties that we consider in the rock properties that we need to understand, and also what we need to understand in the reservoir fluids. So for the reservoir rock, we need to understand the porosity, permeability, fluid saturation, and isothermal compressibility. If you're unfamiliar with these terms, just keep them in mind, and we'll cover them in the following slices. And later on, when you learn more and more about petroleum engineering, those parameters will be repeated in every single time you work in any problem in petroleum engineering, especially porosity and permeability. Then when we talk about the fluids of the reservoir, we mentioned that any reservoir will contain 3 fluids, max, or 2 as a minimum. So we have water, oil, and gas. So water responds to pressure and temperature the changes are not much, and it's not of a high interest for us as petroleum engineers. However, there are some factors we need to consider and learn about it, so we'll keep it to the end. For oil and gas, those are the most two important fluids we have in the system, and we need to understand them, understand how they react and how they behave under different pressure and temperatures, so we can have a better update on our reservoir under depletion. So for gas properties, we'll go over the ideal gas law and the real gas law, and I'm sure you learned those in the thermodynamics. Specific gravity, which is the ratio between the density of the fluid to reference density. So for gas would be the ratio of the gas density to the air density. Formation volume factor, Bg, and the density, the rho g. So formation volume factor, we use it to learn the ratio between the volume, the actual volume at the standard condition, to the volume in the reservoir. Isothermal compressibility, Cg, the viscosity, μg. All these are gas properties that we need to learn, because all those are affected by by different pressure and temperatures, and we need to update our system, our knowledge with it while we deplete the reservoir, to see how those changes will affect my production and how can I manipulate those changes to my benefit to improve the production. Crude oil properties, we need to learn about the solution gas oil ratio, formation volume factor, isothermal compressibility, again, but for oil, and the viscosity, but for oil this time. So let's start with the reservoir rock properties. Porosity. So when we have any rock system, it contains solid parts, which are the grains, and there are the void space between those grains. Imagine you have a pack of salt or a bag of sand, and you pack it in a container. If you look at it from far away, you may feel it's one core, right? It's one block. But you know there are small spaces and void spaces and paths between the grains, right? If you spill or add some water to the sand pack, it extracts so some water will go through the system, right? Go through your sandy grains. Where those water goes through, do they get absorbed inside the grains, or fills those paths and those empty or void spaces between the grains? Yes, it fills those spaces and those paths between the grains, right? And this is the porosity. The porosity is the ratio of this pore volume or those void spaces in the system to the bulk volume, and it's a fraction, and sometimes represented as a percentage. So the porosity, which known by this phi simple, equals the pore volume divided by the bulk volume. Vp refers to bulk volume, and Vp equals Vp, which is a pore volume, plus Vi plus Vs. Vi is the interconnected pore volume, and Vi is the isolated pore volume. So in this in the example I give to you, which is the original porosity, so we have two types of porosities. Primary porosity, which happen during the deposition of the formation, and it can be happen of the intercrystalline, intergranular, and bedding plane, or secondary, which happen after the deposition, such as solution, dolomitization, and fractures, which caused by earthquakes and different other factors. Factors affecting porosity: the orientation or packing, the way the grains are packed. The example I gave to you, if you have different size of the sand grains and you arrange them or pack them in a bad way, you will have less porosity than if you have it in a perfect way. Sorting, how you sort it, cementation, and compaction. All these features affect the porosity. Porosity measurements. There are three ways to measure the porosity. The most common methods are the first two: the laboratory method, which include Boyle's law, the PV1 equal PV2 in equilibrium. Water saturation. We saturate the sample with the water, and then we try to measure the difference in weight and use that difference in weight or mass to get to estimate the porosity, the volume of the void space. And organic liquid saturation, same methodology. Second method is the well logs. Well logs is simple. When we drill a well, we send a sonic or a logging tool, can be sonic or some other tools, where they send waves to the reservoir and receive it, to the rock and receive it, and based on those received logs, we can estimate different properties such as porosity, saturation, and some other properties. CT scan, again, that goes back to the closer method to the first type, which is using a core sample to predict the porosity. Keep in mind that in this class, we're not focused to learn more about how to measure the porosity, the permeability, the rock and flow properties. It's a different class. Most of you took last semester. But the important thing in this part is to get the whole idea, or like the big picture of those characteristics. Permeability. Permeability is a measure of the ease of flow of fluid through porous medium. How conductive is the porous medium? This is what permeability represents. It is described by an equation known as Darcy's law. Darcy's law is Q, which represents the flow rate, equals negative permeability, this is our term, times the 1 over mu, viscosity, times the area, change in pressure over change in length. And this negative is coming from this, because delta P, which is P2 minus P1, we know that the flow goes from higher pressure to lower pressure. So P2 minus P1 will be negative, so we added the negative here to correct for this one. So if you're using this equation and your delta P is P1 minus P2, or the higher P minus the lower P, so in this case you do not need the negative. You always keep this in mind. So for units, if you're using the SI units, so 1 cubic per second equal minus 1 Darcy, centipoise, cubic, squared centimeter, 180 ampere centimeter. 1 Darcy is a relatively high permeability, and we use millidarcy. It's very common in our industry. So 1 Darcy equals 1000 millidarcy. Reservoir rock permeability for conventional reservoirs. If a reservoir has a permeability less than 1 millidarcy, that's considered as poor. For unconventional, that's considered as high and very good. So always keep in mind that we focus on conventional. But if you see some studies that represent permeability in millidarcies and say, oh, this is a very good or great permeability, know that you're reading something in unconventional. Because an unconventional permeability can go to a nanodarcy simply. Fair, up to 10 millidarcy, moderate 10 to 50, good 50 to 250, very good is 250 millidarcy, where you produce simply by drilling a vertical well. Permeability measurements. So here's a simple sketch on the Darcy's law is P1 to P2. P1 is higher than P2, and the flow go from P1 to P2. The equation, so here we get the permeability to the left, so it would equal the flow rate times viscosity times the length divided by the area times the differential pressure. So, and here are the units. If you're using the field unit, which we mostly be using, so you'll need this conversion factor. Let me get the pen, which is 0.00127, and here are the units that you'll be using. Millidarcy, barrels per day, centipoise, feet, square feet, PSIA, PSIA. Okay, so SI unit and field unit. Fluid saturation. The following parameter that we consider is the fluid saturation. Fluid saturation represents the fraction of the porous space that's filled with a specific fluid. So most of the time we'll have water and oil, water and gas, or water, oil, and gas. So we know the pore volume, from the porosity, right? If I tell you the porosity is 30% and my bulk volume is 100 cubic feet, so what's the volume, or what's the pore volume, would be 30 cubic feet. Now I want to know how much of this 30 cubic feet, or how much of this pore volume is filled with water, how much of this volume is filled with gas, how much of this volume is filled with oil. So I think so far by going through these, you may notice that in petroleum engineering, we try to get fractions, right? Or we try to convert volumes and important parameters to a fraction, or based on a reference. That to make it easier, because we deal with many parameters. Because you can simply use the volume of water. You could simply, for porosity, use the volume of pore volume, right? But we always try to get a reference or fraction. So the same thing for the fluid saturation. Based on the pore volume, we can get the saturation. So what's the oil saturation? It will be the volume of oil divided by the pore volume times 100. So that will give you how much percentage of oil do I have in my pore volume. Same for gas and same for water, and the summation of the three would equal 1. So if I have a reservoir which is undersaturated, which means I do not have any cap gas or any free gas in the reservoir, what will be my SG? It would be 0. So then my SO plus SW would be 1. Good. Fluid saturation measurement. There are direct and indirect methods to measure the saturation. The direct approach is the extraction of the reservoir fluids or the leaching of the fluids from a sample of the reservoir rock. We get a rock sample, we extract it, there are 2 different methods to do so, and then we measure how much water we get, how much oil and how much gas, and then we divide this by the pore volume, and we simply have the saturation. Or the indirect method, which is the measurement of some other using some other properties, such as the capillary pressure and the derivation of mathematical relationship between the measured property and the saturation. Okay, there's also a well logging way, which is indirect as well, a measurement of the saturation, but it has its own challenges. So I'm trying not to get into those measurements so deep, because as I mentioned, it's a focus of another class, and we want to focus with reservoir engineering in this class. So the next property we need to consider is the isothermal compressibility. Isothermal compressibility simply describes the change in the volume that substance undergoes during a change in pressure while the temperature is held constant. So when you start depleting the reservoir, all right, the initial condition, you have the overburden pressure, right, which apply external pressure into the reservoir. This pressure goes to the grains, and the grains compresses your volume. And when you start depleting, you release this pressure, right? So the isothermal compressibility is used to measure or to predict the change in volume based on the release in pressure that goes with the depletion process. Okay. So C, which is isothermal compressibility, equal the -1 over V times the change in volume to change in pressure. And the units of it will be 1 over the pressure unit, the reciprocal of the pressure. V is the volume, P is the pressure. So we have isothermal compressibility for the fluids, which we'll talk about later for gas and oil. And there is a pore volume compressibility as well, which is C sub F. At any value of external-internal pressure difference may be defined as a change in a pore volume per unit of pore volume per unit change in pressure. So from this definition, I can use this, or CF, to update which of the previously learned characteristics or properties. So we learned porosity, we learned permeability, we learned saturation, and now we are learning about the isothermal compressibility. So which of these 4 characteristics will affected by the isothermal compressibility? Porosity, permeability, saturation. Porosity based on volume, right? It's pore volume divided by bulk volume. So yes, when I update the volume based on the change in volume to pressure, that will affect my porosity. The porosity should increase. Okay, it's a small amount, but still, it will increase. Saturation will change, because saturation is the volume of oil or the volume of gas divided by the pore volume. Later on, we'll consider also the change in the volume of each of those fluids. Permeability, it will not change, right? Permeability is not a function of the volume. So there is also a very nice straightforward correlation that's stated in the book you can apply to get the isothermal compressibility. And we'll go over it when we come to solving some problems. Now we'll talk about the reservoir flow properties. So now we finished the reservoir characteristics and we'll move to the reservoir flow properties. So I'll stop the video here and we'll continue in another video. So what we'll be covering in this section is the ideal gas law and the real gas law. Equation of a state. So when it comes to talk about the ideal gas law or gas in general, we have to mention equation of state. If you have heard that term before or not, just get a quick reminder. So when we say equation of a state, it's any equation that describes the pressure, volume, temperature, behavior of gas, how they react to each other. What will happen if I change the pressure, how much the volume will be changing, or if I change the temperature. So most of the cases, you'll find that we will have one of those to be constant. So what's the behavior of the volume if the pressure changes at the constant temperature, how the volume will respond to changing in temperature if the pressure is constant. So any of this equation is defined as the equation of a state. There are so many equations of states, not so many, but there are many equations of states. But in this part, we'll go into the simpler one that most of you are familiar with, which is PV equals nRT. We'll go over the specific gravity of gases, really important in petroleum engineering to represent the density of the gas. And again, as I mentioned, in petroleum engineering, we're trying to get a reference for our important characteristics, kind of a ratio. So specific gravity is a ratio between the gas density to the air density. Formation volume factor, which is a BG, and the density. Formation volume factor is a factor that we use to get the ratio of the volume in the standard condition or the surface to the reservoir. How much of a volume in the surface is represented in the reservoir. Isothermal compressibility. So we talked about compressibility in the previous chapter or the previous part for rock, and now we'll talk about it for gas. And finally will be the viscosity. So natural gases are compressible, which make it need more calculations and more consideration than oil and water. Gas properties highly demand on pressure and temperature. Hence, we need an equation of a state. So equation of a state consider those four important gas laws: Boyle's law, Charles' law, Avogadro's law, and J-Lozic's law. As you can notice, in Boyle's law, it considers constant temperature, and we try to measure the relation between the pressure and the volume. If I double the pressure, how the volume will reflect or react. In Charles' law, we have constant pressure and how the volume will be responding to change in temperature. In J-Lozic's law, we have a constant volume, and we want to see how the pressure will respond to a change in temperature. And in Avogadro's law, we consider the number of moles. So at constant pressure, constant temperature, what's the relation between the volume and the number of moles? So considering those four factors, we can get an equation of a state which links the pressure, volume, temperature to number of moles. So ideal gas law states that PV equals nRT, whereas P is the pressure, V is the volume, total volume that gas occupies, N is the number of moles of gas, T absolute temperature, and R is a gas constant. The units of the pressure, volume, the number of moles, and the temperature are directly related to the value of the gas constant that you're using. So in field units, the gas constant units, so we use 10.73, and the units for the gas constant is psi for pressure, cubic feet volume, pound mole for number of moles, and R Rankle for absolute temperature. So you always have to consider this. If you're using 10.73, have to make sure you are using those units. If you're changing the units, so you need to pick another gas constant value. So it's 10.73, and P must be in pounds per square inch absolute, PSIA, V in the volume in cubic feet, N in pound moles, T in degree Rankine. Here's different gas constant values, and here are their corresponding units: pressure, volume, and number of moles, temperature. So 10.732 is what we're using: Rankine, pound mole, cubic feet, psi. Okay. Another value that you may find in some books or chapters or papers that using international units are 8.3145. In those cases, temperature are in Kelvin, number of moles in mole, volume in cubic meter, and pressure in kPa. Ideal gas. What's an ideal gas? In ideal gas, molecules have a negligible volume, and no intermolecular forces is considered. And in this case, we consider no interaction between the molecules to each other, and that makes them ideally behavior. Any real gas, which is not ideal, will behave ideally when or if a distance between molecules are much larger than the size of the molecules, such as low pressure and high temperature. So the further the molecules go from each other, the less they interact with each other, the more ideally they get. Petroleum industry works with a set of a standard condition that we mentioned last chapter, usually 14.7 psia and 60 Fahrenheit for temperature. So we always need to have those values as a reference. Again, for the third time, in petroleum engineering, we love to have reference for everything. Kind of ratio is make the large number of properties that we deal with easier to handle. So when a volume of gas is reported at this condition, always reported at standard condition, it is given the units of SCF. When you report a volume in cubic feet at the pressure of 14.7 and temperature is 60 Fahrenheit, we call it SCF, or standard cubic feet. It's a standard for us. Sometimes the letter M will appear in the units. We discussed it last chapter. MCF means 1,000. MSCF is 1,000 SCF. So what's the difference between CF and SCF? CF is cubic feet. That can be a reservoir condition. That means the pressure and temperature in this calculation was not 14.7 or 60. Where in this calculation is CF, once I see that S, I know that These measurements were done under 14.7 of pressure and 60 Fahrenheit of temperature. And each M refers to 1,000. So if I have 2 M's, this is a million, 3 M's, this is a billion, and so on and so forth. The volume, yeah, this is really important for you to consider, and we'll have an example on it in a second. A volume that's 1 pound mole at standard conditions occupies 379.4 standard cubic feet. So any pound mole under standard condition, which is pressure of 14.7, temperature of 60 Fahrenheit, will occupy 379.4 standard cubic feet. A quantity of a pure gas can be expressed as the number of cubic feet at a specified temperature and pressure, just as this case, right? And also can be expressed as the number of moles, how many moles in a specific volume, or the number of pounds, how many pounds of this gas in this amount, or the number of molecules. When you look in those options, which are, let me get my pen here, either the volume in cubic feet, number of moles, number of pounds, or number of molecules. Which one is easier for you to measure for gases? Can you measure, is it easy for you to measure the number of moles explicitly? No, it will be so hard because we don't see it and it varies with the pressure and temperature. Pounds, can we simply or easily weight the sample, weight the gas? No, same challenge. Number of molecules? Okay, same challenge. So those three, we get them implicitly by knowing the volume that's occupied by the gas. So how many cubic feet does this gas occupying at what pressure and temperature? By knowing the pressure, temperature, and the volume, we'll be able to calculate those three other parameters. And we'll have an example to cover this in a second. So standard cubic feet, we're talking about it. 1 M is 1,000, 10 to 3, 10 to 6 would be mm, to 9 PCF or SCF, and again 10 to 12 would be trillion cubic feet. Keep in mind that all these are SCF, which would be vary than the SCF, right? We discussed it in the previous slides. Okay, let's go in this example to refresh our memory with the ideal gas. Ideal gas load. So calculate the content of a tank of ethane in moles, pounds, and standard cubic feet. So we need to know the number of moles, number of pounds, and standard cubic feet of a tank that have ethane. We do not have enough information. So what else is given? He given us that we have a 500 cubic feet of ethane at 100 psia and 100 Fahrenheit. So we have the volume, right? Volume. We have the pressure. We have the temperature. So we need to use an equation of a state. That's true. So we need to get the quantity in moles, the quantity in pounds, and quantity in standard cubic feet. But before we get into this, or we move from this slide, when we say standard cubic feet, is a 500 under a standard cubic feet? What are the conditions for the cubic feet? For the standard cubic feet or standard condition? Pressure to be 14.7, temperature to be 60 Fahrenheit. So this is not standard. So we'll need to convert this to standard later on. All right, let's see what's needed. Quantity, let's go number one. Quantity in moles. How many moles or how much pounds moles we have? given the volume to be 500 cubic feet, pressure 100 psi, temperature 100 Fahrenheit, which equals 560 Rankine. Because Rankine would equal Fahrenheit plus 460. And why I converted Rankine? Because I'll be using the 10.73 gas constant. What are my assumptions? I assume that my gas is behaving ideally. So I have ideal gas behavior. In this case, PV would equal nRT. R equals 10.73 psi cubic feet divided by pound mole times Rankine. So number of moles in pound moles. Why my units is pound moles? From the gas constant right here. So N would equal, from here, PV divided by RT. Get a laser. So N pound moles would equal 100 psi, the pressure, times 500 cubic feet divided by 1073 times 560. This is not standard condition. So we have 8.32 pound moles under this condition. Second, we need to get the quantity in pounds. So previously 8.32 was the quantity in pound moles. How many pound moles? So number of moles is 8.32. That should be pound moles. And we know that the ethane molecular weight equals 30.07 pound per pound mole. Assumptions are the same. So the molecular weight. Why did they use a molecular weight here? Molecular weight of a substance, and also known as a molar mass, is the mass of 1 mole of that substance, given in mass pounds. Okay, so how much is the mass of 1 mole of this? So I know I have number of moles in pound moles, and I get the mass of each mole. So when you multiply those, you'll get the mass in pound of the moles, right? So mass of pounds would equal 8.32 pound moles. Okay, how many pound of moles do I have? Times 30.07 pounds divided by pound mole equals 250.2 pounds. So the mass of the gas I have in this, under this condition, in the 500 cubic feet ethane tank is 250.2. And as you can see, we get it implicitly by knowing the volume. At standard condition. Is this a standard condition? So 250, is this under the 500, is this under the 100 psi, 100 Fahrenheit? No, this is under the standard condition. Why? Because 30.07, the molecular weight, is considered under the standard condition. Okay, but my 8.32 pound moles was not under standard condition. Would that make any change in my calculation? Let's think about it. I get a gas under a high pressure, high temperature, 100 psi and 100 temperature, and it compressed. Okay, and I tell you that the mass of moles in this tank is 8.32 pounds. When you release the pressure and the temperature to go to 14.7, the volume will change, right? Definitely the volume will change. But will the pound moles change? Will the mass change? Is the mass function of pressure and temperature? No. Mass is not a function of pressure and temperature. Mass is a function of the number of moles, right? If I got a bottle of water, 16 ounce of water, and I filled it with 8 ounces of water, and I weighted it, gave me, let's say, 50 grams. and then I transferred this water into a 2-liter bottle. And I weighted the 2-liter bottle and still contains the same 50 fluid ounce. Do you think you have a different mass? No, it will be the same. So, because the molecular weight is giving us the mass of 1 pound mole under the standard condition, when you multiply it by the moles, the pound moles that we get from the previous equation, we get how many pounds that this mass equals under the standard condition, which is 250.2 pounds. So the third question, or the third need, is the quantity in SCF, standard condition. So we'll use the PV equal nRT. We define the molecular weight. So the volume in a standard condition would equal the pound moles times 379.4, which we covered previously. The volume of 1 pound mole equals 379.4 at the standard cubic feet. Okay, and this kind of constant for all the gases. So when you multiply this by that, units will cancel and you'll end up with a standard cubic feet. So again, this is the volume under the standard condition. Can you calculate it using the ideal gas law? Can you use the ideal gas law instead of the 379.4 standard cubic feet? And you get the same number or close number? Just try to use the ideal gas law. PV equals nRT. Here's N, standard condition, PV, PT, and you need the V, right? So try it, and that will be one of your homework questions. Gas density and gas specific gravity. Gas density is defined as the mass per volume, right? Rho equals M by V. M in pounds, V in cubic feet, so density would be pound in cubic feet. Because weighting gas is hard, as we mentioned, we use number of moles to determine the gas mass. So mass in pound equal number of moles times the molecular weight, which is in pound by pound mole in or at standard condition. So by substituting in this equation, you can say that density equals number of mole by times molecular weight here divided by the volume. So density will equal, by doing the cancellation, the number of moles. We can substitute the number of moles by PV over R divided by RT from the ideal gas equation, right? Times the molecular weight divided by V. Then we'll end up with pressure times molecular weight divided by R times T. Specific gravity. Specific gravity is defined as a ratio of the density of a gas at a given temperature and pressure to the density of the air at the same temperature and pressure, usually near the standard condition. Whereas the density of gases varies with temperature and pressure, specific gravity is independent because the amount of a change to the gas density will be cancelled to the amount of a change of the air density. So it's independent on temperature and pressure when the gas obeys the ideal gas law. Great. Now we had a quick revision in the ideal gas, PV equals nRT, and how can we calculate the volume under the standard condition or under the current condition of the gas, number of moles, the mass of the gas, how we use the molecular weight, which is the mass of one molecule. But we know that in most of the real life cases, we do not deal with ideal gas. It's ideal. Very much it doesn't happen. So in this part, we'll start to learn how can we make changes to the ideal gas equation to fit for the real gas. So real gases act ideally under two conditions: low pressure and high temperature. Real gas. When the volume of a gas will be less than what the ideal gas volume would be, the gas is said to be supercompressible, which makes sense. You compress the gas, so the volume will be less. The number which measures the gas deviation from perfect behavior or ideal behavior is sometimes called the supercompressibility factor, usually shortened to gas compressibility factor. Keep in mind that this compressibility factor is different than the isothermal compressible factor that we mentioned before. Isothermal compressible factor is used to measure or calculate for the change in volume. Gas compressibility factor, or simply supercompressibility factor, is used to define the deviation of the gas behavior from the ideal behavior. So how much does this gas deviated from the ideal behavior according to pressure, volume, and temperature. More commonly, it's called the gas deviation factor, and it's known as Z. The dimensionless quantity usually varies between 0.7 and 1.2 with a value of 1 representing ideal behavior. When Z equals 1, that means the gas is perfectly ideal behavior or behaves ideally. The gas deviation factor is by definition the ratio of the volume actually occupied by a gas at a given pressure and temperature to the volume of it occupied if it behaved ideally. Z equals V actual divided by V ideally. Again, we're talking about the same amount of gas, the same number of moles, the same mass of moles. So P equals VA over Z equals nRT. So PV would equal Z nRT. If you look at this equation, it looks exactly like the ideal equation, except you have the Z, which is a deviation of the volume. Deviation factor, so if the Z equals 1, so the volume is compressed, or my gas is acting ideally. If it's less than 1, so the gas compresses more than ideal gas. So it's smaller in volume than the ideal gas. If it's more, so it's larger than the gas when it's in ideal behavior. So when we look into the real gas behavior of the reservoir pressure on the x-axis and the compressibility factor on the y-axis, here we have one, which is ideally. We can notice that at low pressure, most of the gases, or all the gases, will act ideally. Here we have 3 different gases. This curve represents a gas with a specific gravity of 0.9. So it's heavier than the other gas, which is represented by this curve, which its gravity is 0.665 at 150 Fahrenheit. So we have those 2 gases at 150, and then we have this gas is represented 2 times at different temperatures. So when we want to look at comparing the gases under the same temperature but different gravity, so we look at this one and we look at that one. So you can see that the heavier or the denser the gas is, the more compressible it is. So it's more compressible when it's heavier or denser, because you have heavier materials, so they can easily or faster go to liquid phase or get closer to each other. And when we look at it changing, so the same gas density, 0.65 and 0.65 at different temperatures, we notice that at higher temperature, gases do not compress as much. And that proves what we mentioned earlier, that real gases will always behave ideally under low pressure and high temperature. So we can notice also that at late time, so the peak comes here around 2500 psi, right? But late, around 5000, the gases comes back to behave ideally, but then it will start to increase. So it doesn't compress, actually it shrinks, it expands. And this is kind of super compressibility part. Then we can write the laser tag. Measuring or defining or estimating the Z factor under different pressure and temperatures became a very important topic in petroleum engineering. Standing and Kidd defined and introduced this chart that correlates the pressure and temperature to Z factor. Get the Z factor as a function of the pressure and temperature. But because again the fraction and try to get this unified, they found that when they related or when they get a fraction of the gas pressure to the critical pressure, that defines the pseudo-reduced pressure. So when they use the pseudo-reduced pressure versus compressible factor, they found that all the gases behaves the same, because the compressibility factor is function of the capillary pressure. So when it's included in the equation, that made this universal, and instead of having a chart for every single gas. Same thing for the temperature. So they defined this chart, which is universal and is being used till today, to define Z as a function of the reduced pressure and the reduced temperature. Reduced pressure equals the pressure divided by the capillary pressure. So the higher pressure, you update your capillary pressure, so it will be less PR, and higher temperature is higher TR, and so on. So you do the calculation. But what's PC and what's TC? Those are constants. Capillary pressure, PC is a critical pressure, which is constant. TC is a critical temperature, which is constant. So critical temperature of a substance is a temperature at and above which the vapor of substance cannot be liquefied, no matter how much pressure is applied. So if you see a PT diagram, phase diagram, pressure temperature phase diagram, you see this area where to the right of it, there is no more liquid exists. If you pass this temperature, that's it. You cannot have any liquid. So this line, which is the last line where you have liquid, we call it the critical temperature isotherm. And the critical pressure of a substance is the pressure required to liquefy a gas at the critical temperature. So that's why the critical point. So it's the pressure where the gas will start converting to liquid if you are decreasing the pressure, and if you're increasing the pressure, go from liquid to gas. So those are simply and quickly a definition of the critical pressure and temperature. So if I give you a substance and I ask you what's the Z factor of it, If I provide you with the pressure and the critical pressure of it, temperature, the current temperature, and its critical temperature, you simply apply those two equations, and then you come here, pseudo pressure, you get it from here. Let's say it's 11, so it's right here, or 10. Let me get a pen here. So let's say you calculated this, and that's 10. So you come here in this 10, and you draw a lot. Oh, sorry, I cannot get it straight, but yeah, something like this. And you see here, you get the compressibility factor, right? Okay, what about the TR? Those lines, so each of those curves represent a TR, right? So if your TR is 1.2, which is this one, so you come here, you get the intersect, and you drag it, gets you about 0.55. So that will be a compressibility factor, 0.55. Okay. And you can see it's kind of two charts. So this part of the chart is continuing the chart right here. Okay, so if you can see here, my compressibility, my pseudo-reduced pressure is from 0 all the way to 8. What if it's more than 8? You come down here. 9 all the way to 15. Okay. So, yeah, so in this case, if you are 10 here, the example I gave you, and 1.2 will be somewhere down here. So our compressibility factor will be here, 1.2, somewhere in here. Okay, we'll have more practice in these later. But the one that we did earlier, mistakenly, this one would be correct if my pseudo-reduced pressure is 3.2, okay, not 10. So make sure to separate the bottom one, the bottom part, from the top part. Okay? Okay, what will happen if I have a mixture, a multi-component? The previous example is so simple. We have one gas. I know the critical pressure of this gas. I know the critical temperature of this gas. I will do it. What if I have a multi-component? So in this case, we define the pseudo-critical pressure, which is a function of the composition and the fraction of each component. And we define the pseudo critical temperature, again, which is a function of the components and the fraction of each. Using those, we'll get the pseudo reduced pressure, which equals pressure divided by PC, the reduced critical temperature, and the same thing for the pseudo reduced pressure. And we'll use both in the same chart to get the Z. Here's an example of the component with their formula, critical temperature, critical pressure, and molecular weight. It's in the book. If you need it for any composition, you can simply go back and check on those. Those are universal and well known. So the ethane that we did an example for a second ago, and we used the molecular weight, so it was 30.07 pound per pound mole. Calculating the Z factor. Example 2.2 is a simple, straightforward. I hope you can go through it, and we'll work on it in our synchronized meeting. Should be today. The same thing for example 2.3. Yeah, because there are two ways. The first way is using the chart, and the second way is to use a correlation, an equation, which was developed when the computer started to get involved with more and more in petroleum engineering and in the science generally. So those correlation is straightforward with the book, it's a kind of iteration, and you use it with you can generate a code using Excel or any coding material or any kind of coding language, and you'll be able to calculate a Z factor for using the same methodology. You use the reduced pressure or the pseudo reduced pressure. and temperature. Okay. So, gas formation volume factor. After we learned about the gas compressibility and how can we correct the ideal gas equation for the deviation of the real gas for the real gas. Now we need to use this knowledge to know what's important for us, or one of the biggest problems we face when we work in any reservoir engineering problems, which is link what's going on at the surface, which is a standard condition, pressure 14.7 atmospheric pressure, temperature 60 Fahrenheit, to what's going on in the surface and underground in the reservoir. Let me start with an example. Say you start producing and you know that your porosity is any percentage, but you know that your pore volume is 50 cubic feet, for example. It's a small matter just for the clarification. So 50 cubic feet is my pore volume. And after a month of production, I measured the gas production on the surface and I have found that I produced 100 cubic feet. Does this make sense? Yes. But if you think about it, that I have only 50 cubic feet volume in the ground and I produced more. So if you ignore the pressure and temperature and you ignored the ideal gas behavior on the surface and the real gas behavior on the reservoir, your whole problem would be messed up because you produced a volume which exceeds the available volume in the reservoir. So how can we correct for this? We need to use our ideal gas and our real gas to measure the change. In this, we define the gas formation volume factor. We have my laser pen. So the gas formation volume factor, known as B sub G, relates the volume of a gas in the reservoir, which is the real behavior, real gas behavior, to the volume of isothermal gas compressibility. We talked about the isothermal compressibility when we were discussing the rock properties, and we discussed it as it measures the change in volume that happened because of the depletion or the decrease or the drop of pressure during the production. It affected the pore volume and it will also affect the gas compressibility. So the change in volume with pressure for gases under isothermal condition, which is in the reservoir, V equals Z nRT over P. This is the real gas equation. So then we can say V equals under constant temperature, you can say V equal constant times Zp. That constant is the nRT. N is a number of moles, doesn't change. R is constant, temperature is constant. So those don't change, so this constant is the isothermal, and Cg would equal 1 over P minus 1 over Z, change in Z over the change in pressure. Because Z is directly related to the pressure, because we measure Z by getting the reduced pressure and the reduced temperature. Reduced pressure is equals the pressure divided by the critical pressure. So if the pressure changes, Z also, the deviation factor, the compressibility factor changes. So we need to use this to update for the compressibility. A good question here will be, what would be the difference? Why do I need to use the isothermal compressibility? Or what's the difference between the isothermal compressibility and the formation volume factor? They both measure the change in volume for gas. Formation volume factor updates the volume when the pressure and the temperature are changing, which if you remember from the PT diagrams the phase diagrams that we studied chapter 1, when we had A, for example, reservoir A, we had two paths. The first one was straight, isothermal, going down, pressure drops. And the second condition was going left of the second path, which is decreasing pressure and temperature, which go from reservoir to the surface. So when the pressure and temperature, it changes. In other words, when you compare reservoir condition to surface condition, you need formation volume factor. But if you are comparing the volume in the reservoir when the pressure go from P1 to P2, but it's still in the reservoir and you did not make any temperature changes, you will need to apply the gas compressibility factor. Which one will be larger in change, volume based? Which volume would be larger than the other one? Definitely would be the volume of the surface or the standard condition to the volume of the reservoir. Isothermal gas compressibility, it will be very small compared to the formation volume factor. The question in this slide say, what is the isothermal gas compressibility factor for ideal gas? What will be the gas compressibility factor for this case? Gas viscosity. Gas viscosity of the viscosity of natural gas depends on the temperature, pressure, and compressibility. The units for the gas viscosity is centipoise, and it can be measured experimentally in the lab. However, Carr, Kopaishi, and Boros have developed reliable correlation charts to predict gas viscosity using pseudo-reduced pressure, which we already know how to calculate, and pseudo-reduced temperature in 2 steps. This correlation is very reliable, low error recorded, so we highly depend on it. So what are the 2 steps? There are 2 charts in the book. I think it was 2.6 and 2.7. Let me double check. Yes, it's 2.6 and 2.7. Chart 2.6, we used to get mu1, which is a viscosity under the standard condition. You get the viscosity of hydrocarbon gases under the 1 atm reservoir standard pressure and the reservoir temperature. So you have the reservoir temperature, you see here the reservoir temperature, use the molecular weight of your component or your mixture, and to the left here you have the viscosity at 1 atm or at 14.7 psi. So when you get this, keep in mind you still know that your pressure in the reservoir is not 1, right? So you need to change this M1 to M. So here comes the second step, which gives you M divided by M1, the viscosity divided by the viscosity at 1 atm as a function of the reduced pressure and reduced temperature. So you get the pseudo-reduced temperature and the pseudo-reduced pressure here. You use it, you get mu divided by mu1. Then you multiply what you get from this chart by what you have from this chart, will then end up with having the viscosity under the reservoir temperature, which is considered here from the beginning, and the reservoir pressure, which was corrected for in this chart. Those are straightforward and very simple and used till today in the oil and gas industry. Good morning. Today we'll continue the chapter 2, where we discuss the gas properties, and now we'll move to the crude oil properties. So in this part we'll cover 4 main points that are directly affected by the pressure change in the reservoir and in the surface while depleting the reservoir. First is the solution gas oil ratio, known by RS. Crude oil properties are relatively are different from gas properties. And gas properties, There are reliable correlations with a small level of, or a small error. And also there is kind of a perfect ideality for the gas, which is when it's under low pressure and high temperatures. These cases are not valid or are not expected in the oil cases. Although there are a number of correlations for crude oil, but they're not as reliable as the gases. So having this said, the properties or the mentioned properties in the crude oil are better to be collected from lab experiments, not correlations. But if it's not available, we'll still use the correlations, but we always have to keep in mind that there are many factors that do not make these correlations as reliable as the ones for the gas. So in general, the correlations are not as reliable as a correlation that have been presented earlier for gases. And oils usually consist of many more components. So this is why the correlations are not expected or does not perform as good as those for the gases. Because it has more components than gases, where gases are mostly made up of alkanes, oils made up of alkanes, aromatics, and paraffin. So these affect the correlations, because keep in mind that when we develop a correlation, we test different scenarios within a changeable or within a range of variability for one or two parameters. When you add a third and a fourth and more parameters, that make your the range of efficiency of your correlation less and less. So the mixture of liquid components exhibit more non-idealities than mixtures of gas components. These non-idealities can lead to error in extrapolating correlations that have been developed for a certain database of samples to a particular application outside of the database. Having this said, as an engineer, you should make sure that the application of interest, the correlation that you're going to use for application of your interest fits within the range of parameters for which the correlation was developed. If your interest is beyond those ranges, that means you'll have a higher error and maybe your results will be totally wrong if you apply this correlation. As long as this is done, the correlation used for estimating liquid properties will be adequate and can be expected to yield accurate results. Correlations should only be used in the early stages of production from reservoir when laboratory data may not be available. So that still emphasizes how important is the data work. So before we start producing from the well, we can use correlations based on the pressure, the temperature, expected molecular weight, some other parameters to predict those characteristics. But when we start producing, we need to take some of the produced fluids, either oil and gas, send it to the lab and conduct some experiments to update our properties. And this process is called history match. Black oil. So when you produce oil, you will have, or any black oil in the reservoir, most of the cases will consist of two parts. First is stock tank oil, second is a solution gas. When we say stock tank, we are talking about the surface condition. So I have the oil at the reservoir condition. When I bring it to the surface, there are separation facility. This separation facility will produce gas, and that will be known as gas or free gas or surface gas. And we have the oil that participated or that left in the liquid phase. We call it stock tank oil or stock tank fluid. And solution gas. So in the surface, let's assume this is what we have at the surface condition. We have gas, solution gas, and oil. When the pressure increases, go to the reservoir condition, all the gas will be dissolved in the oil because of the high pressure, and that will be above the bubble point definitely. But you can see how the change happened with the pressure. So we get the reservoir condition, you produce, you get in the separation. This is the stock tank oil, and this is the solution gas. So it's important for us to know how much is this gas dissolved in the oil and how this changed through the production. And always keep in mind that when we talk about production, we're not talking going from this phase, let me get the laser again, from this phase to this. Now we're going that way. We start from high pressure, depleting the reservoir all the way to here. So this will happen in the production bath. And the same thing happens in the reservoir. You may not reach this stock tank condition, which is 14.7 and 60 Fahrenheit, or the standard condition, or whatever the separator condition is, but you may be reaching this level. So that means you start in your reservoir with 100% liquid, and with the production you may start to get some gas. So how can we measure the amount of gas, and how can we use it toward our production development is what we need to do in reservoir engineering. So we have two types of oil reservoirs or oil conditions. The first one known as saturated. These three cases are saturated. What we mean by saturated, that means at this pressure and temperature, the liquid phase cannot dissolve any more gas. It got saturated. I cannot absorb any more gas at this pressure and condition. At this pressure and temperature condition, liquid cannot absorb any more gas. So it's saturated. What happened when a liquid reaches saturation pressure? So it's the same as a bubble point. What happened when the pressure goes below the bubble point? You reach the saturation. So you will start to have some gas phase because the oil cannot absorb any more gases. What if you're above the bubble point? That means, in this case, if I added gas, it will be absorbed in the liquid. So the liquid did not get 100% saturated, and it still have more space to absorb more gas, and in this case we call it undersaturated. And we'll use this terminology later on to define solution gas oil ratio. Solution gas oil ratio, known by RSO, is the amount of gas dissolved in an oil at a given pressure and temperature. How much gas dissolved in the oil, and the units will be standard cubic feet by stock tank barrel. The amount of gas dissolved in an oil at a given pressure and temperature is a function of the pressure, temperature, and the composition of the hydrocarbon, oil, and gases. How to measure the solution gas oil ratio? There is PVT experiments. We discussed it before in the lab experiment, and there are the correlation. So in this lecture, this part, we'll go over the correlations, which we focus on in this part. So at any given pressure and temperature, we need to know how much gas is dissolved in the oil. And you'll see in a second how important it is. Let's look in this chart. This chart shows us the pressure versus the solution gas, or the solution gas ratio, or the dissolved gas amount ratio to the oil. How much gas included in oil. And as you can see here, always keep in mind that when we look in these charts, to look the right way. What I mean by the right way is you going from left to right. Let me get the pen here to be able to draw it. So we go in this direction because we are depleting a reservoir. So you notice that in the first part right here, initial pressure all the way to the bubble point, the RSO, or the solution gas oil ratio, does not change because there is no more gas added, right? We reach the level where the gas is not added. Hamza! When we reach the bubble point, we'll start to have gas leaving the liquid phase to be a gas phase. And the more we deplete, the more gas leaves the reservoir, right? And that leads to a drop in the solution gas oil to the stock tank barrel, because the volume of the oil will decrease and the volume of the gas will increase. So here you know it's constant above the bubble point and it starts to decrease below the bubble point. Again, what's going on here is known as a saturated oil because it cannot absorb anymore, and here it's undersaturated because the correlation for the solution gas oil ratio. When you look in the correlations for the crude oil, you'll notice that most of them depend on the separator data. So we'll start producing, and depending on the production, how much gas we produce in the surface and how much stock tank are we collected in the surface, and specific gravity, temperature, pressure, we can use this to predict the crude oil properties such as the solution gas oil ratio. So this correlation is included in the book, and as you can see, the function of it is to predict the gas oil ratio based on, if you go through the equations, just equation you can apply straightforward using any coding language or Excel or whichever you feel comfortable with. So we use, as you can see here, the bubble point. And how would you predict the bubble point? You can predict it and by a simple separator test, specific gravity as well, and the gravity of a stock tank oil. So how we collect the oil and we get its density, and based on it you get the gravity and the specific gravity from the gas as well. The second property we'll cover today is a formation volume factor known by BO. Formation volume factor known by BO or FVF, formation volume factor, at any pressure may be defined as the volume in barrels that one stock tank barrel occupies in the formation reservoir at the reservoir temperature, with the solution gas that can be held in the oil at that pressure. What that means, before I move to this chart, so we have, let's assume we have one stock tank barrel on the surface. This is how much we produce, right? How much this stock tank barrel is represented in the reservoir, and that will include the dissolved gas, because keep in mind that when you have the oil on the stock tank condition, on the surface condition, you released most of the gas, of the dissolved gas, because you went to the 14.7 or the standard condition. This one barrel will be how much in the reservoir, and it will be always more than one, because when you convert the condition from the reservoir, from the surface to the reservoir, that will be adding to it the gas, the dissolved gas. So formation volume factor equal the volume of the liquid under the reservoir condition divided by the volume of liquid on the surface condition. Okay. This is different than the RS, or the the solution gas ratio, because the solution gas ratio, it tells you how much gas is dissolved in the oil. Formation volume factor tells you how much of this liquid in the reservoir would be represented in the surface. Okay, so if I have the RS of the reservoir under 1000 psi, so I know how much gas is dissolved in this oil under 1000 psi. Okay, when I produce it, this gas will be left. So from knowing the RS, I can know how much of gas will be revealed, right? And then the left amount from this oil in the reservoir condition plus how much it expands, because the liquid expands as well with lowering the pressure. It's not a lot of expansion such as in the gas cases, but it expands by a level. When it's moved to the reservoir condition, that lift amount will be, when I divide it by the initial reservoir fluid plus the dissolved gas volume, that will be my formation volume factor. Okay, so it may feel confusing, and if you still feel confused about it, let me know and we can elaborate it more. But always keep in mind that the formation volume factor is always above 1, not because the volume of the oil on the surface is smaller than the volume of the reservoir of the fluid in the reservoir. Because when you increase the pressure, the volume on the surface will be higher than the volume in the reservoir. Because we increase pressure, we decrease the volume, right? But what makes it more than 1, which means the volume on the surface is less than the volume in the reservoir, is the fact that we have a dissolved gas. Okay, that will be explained more right in this chart. As you can see here, we start. Okay, let's go the backwards. We go from the surface here. So we increase the pressure. You can see the formation volume factor increases. Okay, because the amount of gas decreases up to the bubble point pressure. After the bubble point pressure, we don't have any gas. So if I have 1 barrel in the reservoir, okay, condition, the amount of gas is constant at this point to this point, right? So what happens when the pressure increases? We do not add any more gases, so the volume of gases does not increase. However, the oil is compressible to a limit, and that causes the formation volume factor to decrease above the bubble point. Okay, so if we have the chance to add more gases, the curve will be continuing up. The correlation for the formation volume factor, again, is in the book, chapter 230, and it's a function of the pressure. So if the pressure is less than the bubble point, we use this equation, and again, you can see that we're using the properties collected from the separator: stack tank oil, the average specific gravity of the gas, and the oil density. Specific gravity in this equation will apply when the pressure is above this one to get the specific gravity of the surface of the gas. So I don't go deep in the correlation because it's not the focus of this class. But it's always good for you to get a feeling of your tools. If I don't find this in the report it to me, or if I don't have access to this data, I always can use a correlation, and you know where are your correlations. If the pressure is above the bubble point, we will be using this correlation. Total formation volume factor. Total formation volume factor, and also known as a two-phase formation volume factor, which is defined as a volume in 1 barrel, 1 stock tank barrel, and its initial complement of dissolved gas occupies at any pressure and reservoir temperature. The total formation volume factor counts for the formation volume factor, or the volume of the oil in the reservoir to the volume of the oil on the surface, plus the formation factor, the formation volume factor for the gas as well. So we know at any condition, we have BO, or we have the oil, and we have the dissolved gas. We can get the dissolved gas by subtracting the initial dissolved gas minus the dissolved gas in this condition. So if I started with 100 cubic feet dissolved in 1 barrel, and after I produced a little bit my so at, let's say 2000 psi. When I moved to 1000 psi, my solution, my RSO, the solution or dissolved gas became 50. So that means in my 1 barrel liquid, I have 50 dissolved gas. So how much gas is released from the pressure from a 1 barrel when I move from 2000 to 1000? That would be the 100 I started with, the initial, minus the 50, right? So the released is 50. And to get the total formation volume factor, we count for this amount, okay? Because this gives us how much of RSO is left, plus the change in, or the ratio of the oil, give us the total formation volume factor. Isothermal compressibility, we covered it for formation, for gases, and the same exact idea for the oil. It's the change of volume as a function of the pressure. Oil are not highly compressible, but they show a level of compressibility, and we can measure it by applying this equation, 1 over V times V delta V over delta P. And there is a correlation as well in the book. I encourage you to go over it, to be familiar with it for your future plans and for future career. We finish the rock properties, oil properties, and gas properties that we'll need and will use during this this lecture or this class of reservoir engineering. There is water properties. Okay, that would be one of your assignments to read through it. So when we talk about the water, there are 2 main characteristics we have to consider. The first thing is the volume of gas dissolved in the water. It's not much. Most of the time we ignore it, but there are a level or an amount of gas dissolved in water. Second is the viscosity of water, okay, which will change with the pressure and temperature, same as the oil. So by reaching this, we finished chapter 1, chapter 2. There will be homework assigned. I hope you read chapter 2 and finish it. If you have any questions, contact me, and I will see you in the lecture. I'll be sending notifications. Stay safe and have a good day. Okay, by reaching here,